Right, this problem has a solve, and in this case we're solving for z. It's the only variable here. You'll notice there is a z squared, so there is potential for quadratic methods to come to play, either square roots or factoring, perhaps the quadratic formula, but we'll work through it and see where we get. Also, there are two fractions on the left-hand side of the equation, so to tackle those, if we could get them to a single fraction with a common denominator, we could multiply the denominator to both sides and make it a single line equation. So that's where we'll start. If you'll notice, they're kind of common, but they're not exact. The denominator on the second fraction can be factored into z times z minus 5. And then that you would have a z minus 5 common to both of them. So the only thing you would have to do to the left one is to multiply both the numerator and the denominator by a z. So if you do that, you don't have to do anything to the 3 because you didn't change the entire equation. You only changed that first term the way that it looked. You didn't change its quantity. So what we have now is a 21z over z times z minus 5 minus 13 over z times z minus 5 equals 3. Common denominator exists now between these two fractions on the left, so we're going to simply subtract across the top. It's not really much to do, just to write 21z minus 13 all over z times z minus 5 equals 3. Now we have a single fraction on the left and a single quantity on the right, so I can multiply both sides by the z times z minus 5 just once. Z times z minus 5. Those are z's, not 2's. You don't distribute anything on the left. It cancels the denominator. That's the whole point. So we have 21z minus 13. This will end up being, see, that's z squared minus 5z, and then the 3 will distribute to those. So that equals 3z squared minus 15z. The fact that there remains a quadratic as well as a z with a single exponent of 1, this will best be solved if you just set that polynomial equal to 0, and then we'll look at our quadratic methods. So I'm going to subtract the 21z and then add the 13 and do both of those terms over to the right. And then what you'll have is that 0 equals 3z squared minus 36z plus 13. Right, so we do have a quadratic. None of those three terms have a common, like a greatest common factor. You could factor out, try to make it nicer to deal with. The z squared coefficient is not 1, it's a 3, so it makes it a little harder to factor. And you're welcome to sit and try your trial and error of the two factor pairs. You know, it's going to be at least a 3z and a z. The 13 is positives, the middle is negative, so they're both negative. And then, I mean, you could try 13 and 1 or 1 and 13, but I don't think this is going to factor. So unless you'd like to go through completing the square, which I'm happy to show you at another time, I'm going to go ahead and use the quadratic formula for this. So what I'm going to do is recopy this equation. If it will let me. It might not let me. I'm just going to rewrite it then. How about, so we had 0 equals 3z squared minus 36z plus 13, and we're trying to solve. If you recall the quadratic formula, it was x equals, but in this case it'll be z equals. It was negative b plus or minus the square root of b squared minus 4ac all over 2a, where a was the coefficient on x squared, b was the coefficient on x, and c was the constant that was added or subtracted. And just make sure you pull the right signs with those. In this case, a will be 3, b will be negative 36, and c will be positive 13. So if we take and we plug our coefficients into quadratic formula, we get that z should equal negative of the negative 36 plus or minus square root of negative 36 squared minus 4 times 3 times 13, all under the square root. and that all gets divided by 2 times 3. All right, so clean up. We've got a positive 36 plus or minus. If you do that quantity of negative 36 squared minus 4 times 3 times 13, the product comes out to be a 1,140 all over 6. If you recall from square roots, you can't really leave it that way. So you have to try to figure out, well, can I simplify it? Does it have any perfect square factors? At least that's how I've always taught this. Take 1140 and divide it by perfect squares, like 1140 divided by 4, 1140 divided by 9, 1140 divided by 16. 1140 will actually divide by 4. So if I take the square root of 1140 and I break it apart into 4 times 285, then I can break apart those square roots. There's just a square root product property, and that would simplify to 2 times the square root of 285. And that's what I will put in place of the square root of 1140. So 36 plus or minus 2 times the square root of 285 all over 6. And the very, very last step in simplifying anything with quadratic formula fractions in particular is the fact that there's 3 regions that all have a common factor of 2 in them. You can't touch the 285 because it's under the square root, but those 3 regions, if they have a common factor and it has to exist in all 3 regions, then you are more than welcome to divide that away. So 2 into 2 is 1, 2 into 6 is 3, 2 into 36 is 18. And what this finally simplifies to is 18 plus or minus the square root of 285 all over 3. That is the actual answer. It is simplified. It is irrational. It would be a decimal that does not have a pattern, but most likely you would be asked to do exact. And what the software with Wiley usually asks you to do is 18 plus square root of 285 divided by 3, comma, 18 minus square root of 285 divided by 3, unless it allows you to use the plus and minus. But we'll just have to see when we get to those types of problems. But that is how you solve that, that equation that you had back in the beginning.